These logs are going viral. Lesson 7, ready, set, go. The last section of Unit 2. So glad you're here. Congrats on making it this far. We have the ready asking us to fill out this table or 4 with some values. Y equals just x to the first power. Pretty simple. Whatever x is, that's what y is. So if x is -2, the outcome is -2. If x is -1, the outcome is -1. 0, 1, 2, so on and so forth. Now squaring x, so now getting +9. -2 times -2 gets you +4. +1, 0, and then rinse and repeat. So those tables, just plug and chug, really. You get some x cubed now. So notice it's an even exponent. Maybe there's some inconsistency with just staying a positive, or it might fluctuate. So -27, -8, -1, we hit 0, and now we bounce back to a happier time of positive numbers like 8 and 27. You haven't had to graph out anything to the 4th power before, but take your time with this. This is going to be 81. This is going to be 16. This is going to be +1, 0, 1, 16, 81. Capiche? You have all of these graphed out. I'll leave it up to you to label each one. Identify the points that they all share in common. Well, I think they all hit 0, 0. If we look closely, all 4 lines should hit 0, 0. And I believe that they all hit 1, 1. Why is this logical? When you keep multiplying 1 by itself over and over, so multiplying by +1 over and over can only produce an outcome of 1. And also 0 to any power is just going to be 0. So that's why they're all on there. I'll leave 7 for you. We have certain bacteria population known to double every 15 minutes and experiments being conducted in microbiology in the lab that's there. Suppose there are initially 7 bacteria in a petri dish. Make a table, graph, an equation that will predict the number of bacteria in T hours. Well, key element here is that it's every 15 minutes, which is a quarter of an hour. And so maybe let's back it up a little bit. At 0 hours, we have 7. When we head to a quarter of an hour, this is now doubled. Getting us to 14. Let's hit it again. Another 15 minutes pass, which is half of the hour now. So double again. 28. I'll give you a moment to fill out the rest of this table, and then we'll talk equations. Hopefully you got these values. Let's jump ahead and just make the equation. So I know that we were talking in increments of the quarter hour before, which is cool. I'm going to, however, just jump to like the main idea of like, what's it per hour? So starting at 7, run this arithmetic real quick, but you'll see that this keeps multiplying by how much? You guessed it, 16. And that's for every hour. And you could even change this up if you wanted to. You could say that this is 7 times 2 to the 4th t, if you're more of a quartered person. And then you could eventually say that this is also another way that the equation could be rewritten. So this works just fine. This works if you wanted to focus more in on like how there are quarter hours to accommodate. But this is pretty much every hour what's going to be happening. It multiplies by 16, but at every quarter of the hour, it multiplies by 2. Capiche? Graphing, I can leave that up to you. The equation we just got, Between what times to the nearest quarter of an hour will the bacteria exceed 10,000? So maybe let's make a little equation for this. So we want to find out when this equation is going to be greater than 10,000. We haven't had to really use an inequality for this before, but we're totally capable. So think of this as just like solving a normal log function or exponential function, claiming that 16t is now greater than this fraction here. And yes, you can go back to log form, so go for it. And this is going to say that the number of hours is approximately log 16, 10,000 over 7. And I will calculate that for you in a second. So with the powers that be, this is going to be approximately 2.62 hours. And if you go to the quarters of the hour, it's going to be lying between 2 hours and 30 minutes, but definitely less than 2 hours and 45 minutes. So it happens in that time frame. Capiche? Makes sense. B, I'll leave for you. What else? Predict the number of bacteria after 24-hour period. I mean, you could just plug in again. Does this like change or something? What really changed? Is this just pushing you to ballpark it after 24 hours? Because I mean, you have the equation. Yeah, so you could just ballpark this and I'll leave that for you. Right, the logarithmic equation that would allow you to find time t when there are 700 bacteria. I mean, you could set it up claiming that this should equal 700 and you just have this. So you could take it further. You could divide by 7. That gets you 100, and that equals 16t. So eventually, when you go back to log form, you're going to have log base 16 of 100, and that equals your time that there should be 700 bacteria. Capiche? Make sense? What concludes? You get some throwbacks. This is definitely going to be on the test. So know how to do these problems. Some of these you might have to be strategic. Like you don't have 2 or 3 here, but out of the numbers that are here, do you think you can make a fraction of 2/3? What do you think? Hopefully you're saying that you could use 8 over 12. That could work. You could then use the, you guessed it, quotient rule. And say that this is really just log 8 minus log 12. You have the arithmetic for that here. So just take it further. 0.9 minus 1.1, getting you negative 0.2. Are there any other tough ones here? I mean, 1 over 7, you could really say that this is just log of 7 to the negative 1 power from the, you guessed it, exponent rule. You're allowed to say that negative 1 bops to the front, multiplies with what's left. So negative 1 times log 7. So really it's just negative 0.8. Kind of a cool one there, pushing you to use negative exponents. What else? This one's pretty simple. This one may be a little tough. Maybe let's think this one out. Let's be a little strategic. We have 3 over 14. Well, I know that 7 could probably amount to that. So you maybe, let's break this apart. Say this is going to be 7 times 2. And this is just prime, so it's 3. But let's see if we can like get this up the ante so that some of these numbers appear. Well, I know that if this up here was 12, that could work. So maybe if I multiplied here and here by 4, this now gets you 12. And did I just finish the problem? Yeah, I did. Okay. So if you take this further, this is really claiming 12 over 7 times 8. And of course, we're talking about the argument and how that argument can be rewritten. So really, you could just say that you're solving for this. So say that it's log 12, subtracting, I'm going to use brackets here around these two, log 7, and yep, product rule says we have to add these two. So plus log 8, close it up with a bracket. I use the brackets if it looks as if I'm going to like subtract quite a bit in the denominator. So I suggest that you do the same. And you could even run the arithmetic from here and say this is 1.1 minus 0.8 plus 0.9. And if you take this further, it's really just 1.1 minus 1.7. So negative 0.6. So luckily we were a little strategic. Luckily the numbers were easy to rewrite. Notice how 3 and 14 don't quite match what's here, but if I multiply the top and the bottom by 4, I created 12 up here and then a makeshift 8 down here, which matched what I knew. So I hope that this video was helpful. If you got any questions, bring them to class. Thanks for making it this far into the video. Take care. Brush your hair.